Okay, so next section 3.2 is on the norm, the dot product, and distance in Rn. So what is the dot product? The dot product between two vectors is you take each component of the one vector and you multiply it with its corresponding component in another vector, and you add all these products together. That's the definition of the dot product. Now, to be able to take the dot product between two vectors, we need these vectors to have the same number of components. And also note that the dot product between two vectors is a real number, it's a scalar. Okay, there are two examples of the dot product. The first one is written out. You multiply each component with its corresponding entry in the other vector and you sum them all together. Now I'm going to leave the second example for you guys to do. Okay, next note that if you take the dot product of a vector with itself, it's simply by definition the sum of the squares of the entries. And theorem 1 basically just tells us how the dot product behaves. If you have three vectors u, v, and w and Rn and see a scalar, then you have commutativity, you have distributivity. The dot product works just like normal multiplication in that it distributes over the sum. And also with regard to scalar multiples, if you take a scalar multiple of a vector and you dot it with a vector v, then it's the same as dotting u and v together and then multiplying that with the scalar c. And then the last one tells us when the dot product of a vector with itself is 0, and that happens only when the vector itself is a 0 vector. Okay, let's prove that distributivity law. It's not terribly hard to prove it, but it's just a good dot product exercise. So you're asked to prove that what we're going to do is you're going to note the following. You're going to note that if you look at the dot product of u with the sum between these two vectors, v and w. Now, if you're going to just write that out, you're going to get, first we'll write the vector v plus w out, and that is going to be the vector with first component, v1 plus w1. It's going to have second component, v2 plus w2, and the last component, Vn plus Wn. Alright, so that is my first, those are my two vectors, and then it's just application of the dot product. So that's going to be u1 multiplied, the first component of u multiplied by the first component of v plus w plus the second components multiplied together. Okay, plus then the last component multiplied together. Okay, so multiplying that out, you get u1 v1 plus u2 v2 plus un Vn, and then you have the other one that you have is u1 w1 plus u2 w2 plus un wn. Okay, and so that is just that this whole thing here you can just write as the dot product of the dot product of which vector is that? The dot product of u with the vector v. Okay, and this thing here, that is just the dot product of u with w. Okay, so pretty straightforward. Okay, let's prove theorem 1.4. Theorem 1.4 states that the only way that a vector is the zero vector is if its dot product with itself is zero. So in this case, we first assume the dot product of u with itself is zero. Thus, we have that u's dot product with itself, we know that's the sum of the squares of the components. Okay, and that is zero. Now u1, u2 up until un, these are all real numbers, and if you square them and sum them together, the only way that the sum of positive real numbers is zero is if each one of the terms is zero. So the only way this can happen is if ui is zero for all indices between 1 and n. So we have that u, which is this vector here, u1, u2, un is going to be the zero vector. Okay, so that is proving from left to right. So let's look at the case where we prove from right to left, like assuming that u is a zero vector. Let's quickly show that the dot product of u with itself is zero. Proving from right to left is a straightforward exercise. We're going to say we're going to let u bar be 0 bar, meaning that u is the zero vector. We have that each component of u is zero. Okay, and from that, it's then easy to see that the dot product of u with itself is going to be the zero vector. So that's the first component multiplied by the first component plus second component multiplied by the second component plus the last component multiplied by the last component, and that is just 0. Okay, so that proves theorem 1.4. Okay, so length, the concept of length in vector spaces. So the length or the norm of a vector is simply the it's the square root of the sum of the squares of the components. So what you can see the norm as a function from a vector space to the positive real numbers, where the function maps each vector to a real number, which is its length. Okay, that brings us to theorem 2. So V is a vector in Rn and C is a scalar. Then theorem 2 says the norm is always positive. The only vector that has a zero norm is the zero vector itself. And if you take a scalar multiple of a vector and you take the norm of that, then it's simply the absolute value of the scalar multiplied by the norm of the vector. Okay, so let's investigate the concept of the dot product and the norm. If you have a norm, the norm is actually a function that maps a vector to the set of positive real numbers in our case. So I just want to illustrate this in 3 space. The 2 space and n space case in general uses the same argument. So here, let's look at 2 vectors in 3 space. Okay, so I'm going to denote point P, U1, U2, and U3. And I'm going to denote the other point Q by V1, V2, V3. Okay, and we have our vector there, which is called the vector U, and I have my vector there, which is called the vector V. All right, and we've got the angle between those two vectors given as theta. Now there, that vector there is the vector u minus v. Now there was a formula for the triangle, for the length of the edges of a triangle that we did. We used Cramer's rule. It's a well-known formula. So remember we said that the cosine of the angle theta is going to be 2 times the length of the one edge, which in this case is the norm of the vector u, okay, multiplied by the norm of the vector v, right, which is the length of the vector v, and then we have that on top there we've got the norm of the vector u squared plus the norm of the vector v squared, okay, minus the norm of the vector u minus v squared. Alright, so that is going to be basically 2 times the norm of the vector u times the norm of the vector v times cos of theta, and that is going to be the norm of u squared plus the norm of v squared minus the norm of u minus v squared. And from there you can now go and just solve this expression here. Okay, so I'm going to get an expression for the norm of u times the norm of v times cos theta, and that is just a half of this whole expression. Now the question that I have is, what is this expression in the bracket? What is that actually equal to? You can do a simple, you can do a little bit of algebra, which we're going to do now, and see what that reduces to. Okay, so the question is now, what is this expression actually equal to? Okay, so what you have is, you've got the norm of the vector u squared plus the norm of the vector v squared minus the norm of the, remember we said the vector u minus v, so that's going to be the vector u minus v squared. Now if you go and look what that is, what's the norm of u? It is u1 squared plus u2 squared plus u3 squared. And what's the norm of v? It's v1 squared plus v2 squared plus v3 squared. Remember, the norm measures the length of the vector. And this term here is going to be, what is the norm of that? It's going to be u1 minus v1 squared, okay, plus u2 minus v2 squared plus u3 minus v3 squared. Okay, and then doing some simplification, you're left with u1 squared plus u2 squared plus u3 squared plus v1 squared plus v2 squared plus v3 squared. Okay, minus, so you've got your square terms there, u1 squared plus u2 squared plus u3 squared. Okay, and then you've also got your v terms, right? So you're going to have plus v1 squared plus v2 squared plus v3 squared, okay? And then you're going to have minus 2u1v1 minus 2u2v2 minus 2u3v3, okay? And then, just simplifying that, all the square terms are going to cancel out, and you're basically going to basically be left with twice u1v1 plus u2v2 plus u3v3. All right, which will then imply that if we go back to our previous statement, this term here is basically going to then be that term is basically then going to be this here. So you've got u multiplied by v's norm multiplied by the cosine of the angle between those two vectors is going to be a half times 2 u1 v1 plus u2 v2 plus u3 v3. Okay, so that is just going to be what? u1 v1 plus u2 v2 plus u3 v3. Okay, and what is this thing here? This is the definition. That's the definition of a dot product. So essentially what they're saying there is the dot product between the vector u and v is going to be the norm of the vector u multiplied by the norm of the vector v multiplied by the cosine of the angle between the two vectors. And you can also make the following observation, that if you have also note this following thing, because we're going to get to it later on. What you can also say is that if you look at remember the dot product is a real number, so if you take the absolute value of that, right, the norm is already a positive number, okay? Cos of theta, okay? And what is the biggest that can become? The biggest this cos of theta can be is basically, or the absolute value of cos of theta is, the biggest value it can take on is 1. So this inequality is a well-known inequality. It's called the Cauchy-Schwarz inequality, and then we'll get to that later in the notes. Okay, so also just take note of this inequality. So all these things are related. Okay, let's look at quickly at the proof of theorem 2.2. That's an application of the previous theorem, the point 4 that we proved. If we assume that the vector v has norm 0. Okay, so essentially the length of that vector is 0. So what we want to then show is that it's the 0 vector. So we have that essentially the norm of this vector we know is the square root of the dot product between the vector v and itself. And this is going to imply that because the norm of this vector is the 0 vector, and that is equal to the square root of the dot product, that's going to imply that the dot product between the vector and itself is going to be 0. And we know that this implies that if the dot product between a vector and itself is 0, then the vector is going to be the 0 vector. Okay. Right, now if v is the 0 vector, then we know from our previous theorem 1.4, we know that the dot product of v with itself is going to be 0, which is going to imply that the square root of v with the dot product of v with itself is going to be also 0, which then implies that the norm of v is going to be 0. Okay, so that's an application of theorem 1.4. Then proving theorem 2.3, that is also just quick exercise on the norm. What we do there is you can note the following. If you take the norm of the scalar multiple of the vector v, right, then that is going to be it's going to be the norm of this vector here, where you take the scalar and you multiply each component with the scalar. Okay, and then it's just pretty much applying what the norm actually is. So the norm is just the square root of the sum of the squares of the components. So that's going to be c squared v1 squared plus c squared v2 squared up until c squared vn squared, and that is going to be c squared multiplied by vn squared plus v2 squared plus vn squared. It's going to be the square root of that. Okay, so that then is going to be, if you take the square root of c squared, that is going to, well, c squared is going to make c positive, and so you're going to be left with the absolute value of c multiplied by the sum of the squares. Okay. Okay, and that is going to be the norm of the vector v. Okay, so very quickly, I'll do example 2. You guys can do example 1. So what is the norm of the vector u? The norm of the vector u, remember, is then just simply the square root of 3 squared plus 0 squared plus minus 2 squared. Okay, and that is the square root of 9 plus 4, which is the square root of 13. Okay. Okay, so you're given 3 vectors and C is a scalar, and explain why those expressions make no sense. This is just to test the understanding difference between a dot product and vectors. The first one there doesn't make sense because you're taking a norm of a quantity that's not a vector. The second one, you're adding a dot product to a vector, so that doesn't make sense because you're adding a scalar to a vector. The third one, again, is you're taking a dot product of a vector u with a dot product, which is not a vector. The last one there is we're taking a dot product between a scalar and a vector, and dot products only work between vectors, so that also doesn't make sense. Okay, next we have a definition. A vector of length 1 is called a unit vector, and finding a unit vector in the same direction as a vector is called normalizing the vector. This is done by factoring a vector by its length. In other words, you're taking the vector, you're taking a scalar multiple of that vector, and the scalar in this case is 1 over the norm of v. Now, looking at that example, if we take the vector u, then you can easily see that it's a straightforward process to calculate the norm of that vector u. And then once you have the norm, you take 1 over the norm and you multiply it with the vector u. And that new vector you get will be a unit vector. In other words, it will have norm 1. Now, why is this so? We'll investigate this in the next little clip. All right, I'll leave the example for you to do on the bottom of the page. Okay, let me explain what it means to normalize a vector. So normalizing a vector means you take the vector and you change it into a vector that has norm of 1. Now, if you look at the vector, a vector, so if we look at this vector here in n space, v1, v2, vn, right? And we take the norm of this vector. Now we know the norm of this vector, it measures the length of the vector. So we know that this is the square root of the sum. Right. Now, if we take this vector v and we multiply it with a scalar, right? Let's multiply it with this scalar. Remember, this thing here is a real number. So it's a fixed number. So we take the scalar multiple of the vector v. Okay, now what is the norm? What is the norm of this scalar multiple? What is the norm of this scalar multiple? Okay, we know from norm theorems. Remember, there was that little result that we did that says that if you take a scalar multiple of a vector and you take the norm of that, that's going to be the absolute value of that multiplied by the norm of that vector there. So that was that result we did. So applying this result, you then have that that this is in fact given by that expression there, and that then becomes the number 1. So so basically you can normalize any vector by multiplying it with the scalar 1 divided by the norm of the vector, and that changes it into a unit vector. And sometimes we want to normalize a vector because it just makes it easier to work with unit vectors. Okay, so there we have standard unit vectors definition. In R2, the standard unit vectors are 1, 0, and 0, 1 respectively. In R3, it's 1, 0, 0, 0, 1, 0, and 0, 0, 1 in R3. And in general, we can extend that idea to Rn, where the vector in the ith component will be 1 and all other components will be 0 for all indices I between 1 and n. Then there at the bottom of the page, also note that you can express any vector, for example, in R3 as a sum between scalar multiples of unit vectors, of the standard unit vectors. So you can express v1, v2, v3 as a scalar multiple of the first standard vector plus a scalar multiple of the second standard vector plus a scalar multiple of the third standard vector. Theorem 3, the Cauchy-Schwarz inequality, we already proved this result earlier, and I'm bringing up there that old slide where you could see the inequality. And from that, we can actually derive the triangle inequality, which is a very important result in mathematics. For all vectors u and v and Rn, the norm of the sum is at most the sum of the norms. Okay, so this is a very, very important result. I would just want to quickly look at the proof of Theorem 4. Okay, I want to look at the proof of the triangle inequality quickly because it's a nice application of the distributive law of the dot product. And it proves it's an extremely important inequality in mathematics. So if we look at the square, if we look at the square of this norm of the vector u plus v, then that is going to be, remember by definition, it's going to be the dot product of the vector u plus v with itself. Okay, so it's going to be the dot product of those two vectors. Now we know by the distributive law, we have that's going to be the u's dot product with itself plus 2 times the dot product of u with v plus the dot product of v with itself. Okay, so by definition, that is going to be the norm of the vector u squared plus twice the vector u dot with v plus the vector v's norm squared. And that is at most. Remember, we use the Cauchy-Schwarz inequality, which is this inequality here. So what is the biggest that this whole expression can become? Well, it reaches a value of at most this, right? So because the dot product can be negative. Okay, so making it positive, that'll always be bigger. And by the Cauchy-Schwarz inequality, that's going to be even at most this little result here. So it's going to be, you're going to plug that in. So you're going to get the norm of u multiplied by the norm of v plus the norm of v squared. Okay, so we going to factorize that, and that just basically becomes, that's going to become the norm of u plus the norm of v squared, which is then going to imply that we have that our inequality holds, because the square of the norm of u plus v is at most the square of the norm of u plus the norm of v. So taking square roots on both sides, you have positive numbers, so you're not going to have a problem there with the inequality switching over, possibly. So there you've got your triangular inequality. This is a very important result in mathematics. Okay, next we have distance. The distance denoted by duv denotes the distance between the vectors u and v. And it's simply defined as the norm of the vector formed by taking u and subtracting from that the vector v. We already know what the norm looks like. So if you take that example 1, 2, 3 and 2, 3, 1, it's easy to calculate the difference between those two vectors, u minus v. And then it's a straightforward application of the norm function to calculate the distance between the two vectors. So I'm leaving that example on the bottom of the page for you guys to do. It's straightforward application. All right, Theorem 5, the triangle inequality for all vectors u, v, and w and Rn. That inequality holds. Distance between u and v is at most the distance between u and w plus the distance between w and v. So it's not hard to prove. We know that the distance between u and v, we know that that is the norm of this vector u minus v, okay? And that is equal to, what you can do is you can go and subtract the vector w, and you can go and add the vector w without changing anything there. Okay, and now it's just a straightforward application of the triangle inequality, because this is according to the triangle inequality, this is at most this plus this. Alright, and that is equal to the distance between the vector u w plus the distance between the vector w and v. Okay, so that is a straightforward application of the norm triangle inequality. All right, next we have angles. We already did derive this formula earlier in the lesson. If you have two vectors u and v and Rn, then the cosine of the angle between the two is simply the dot product between the two vectors divided by the norm, the product of the norm between the two vectors. So I'm just bringing up that slide. We'll see there in that first line earlier we did derive the formula for the cosine of the angle between two vectors. So I'm leaving that example at the bottom of the page for you guys to do on your own, just applying that in. I want to look at a more hands-on problem in what's going to follow just now. Okay, so let's look at the example. Find the acute angle between the planes x plus y minus z equals 1 and the plane x equals 0. So I want to just look at what does this plane more or less look like. So I'm going to consider the xz projection. I'm going to consider the xz projection. So here you've got your y-axis. Sorry, your z-axis, and then you've got your x-axis. So looking at the xz projection, we make y 0. So we're looking at the straight line x minus z equals 1. So that's going to give you 2 points. It's going to give you a point there of 1, 0, 0. And it's going to give you a point there. The point 0, 0, minus 1. Right, so there we've got more or less an idea of what this plane is going to do. All right, so now we look at the XYZ environment. So there we've got the Z axis, we've got the X axis, and there we've got the Y axis. So there we've got the Y, there we've got the Z, and there we've got the X. So let's just quickly see what this thing looks like. So there we've got the point there, and we said that point is 1, 0, 0. There we've got the point. We said that point is 0, 0, minus 1. Okay, so we've got that line there. And then we can also look at the ZY projection by making x 0. And we're going to get a point there, which is the point 0, 1, 0. So I've got it there. And then basically if you look at the YX projection by making Z 0, we've got the line y equals 1 minus x, and so we've got this straight line here. Okay, so basically just to get, we're only drawing this like small section. So here you've got your x, your ZY plane. Okay, there we go. And so there we've got what we're looking for, and there Just shading it a bit to get a better look of what is going on here. Okay. All right. So what is the angle that I'm actually interested in? So the angle that I'm actually interested in is this angle. It's this angle here, which is this, basically that angle there. All right. So going back now, we can label that point P and that point Q. Right, so what is if you look at the vector PQ, all right, we know that is the vector. Remember how we define this vector? It's the vector 1 minus 0, 0 minus 0, and 0 minus 1, which is 1, okay? Right, so that's the vector. This is the vector PQ. Right, and now we can just choose the unit vector in that direction there. All right, and we'll call that the vector V. Okay, so we can then go and then just go back to our original system there. So this is a vector PQ. We go and place it at the origin. So that's my vector PQ. Okay, and that is my vector V. Vector V. Okay, and that vector V there is, I'm just going to just indicate that as the unit vector in that upwards direction. All right, so what is the angle then between those two vectors? That's the angle I want there. That's the angle there. Right, so we're going to just call that theta. So we know that cos of theta is going to be the dot product between the vector V and the vector PQ, and that you're going to have to divide that by the norm of the vector V, which is a unit vector, all right, and the norm of the vector PQ. Okay, so that then becomes, we know what V is, and we know what PQ is. Now V is the unit vector in that direction, and PQ is the vector, we said 1, 0, 1. Okay, and what is the norm of this unit vector? It's 1. And what is the norm of the vector PQ? The norm of the vector PQ is square root of 2. So that dot product then becomes 0 times 1 plus 0 times 0 plus 1 times 1, which is basically 1. So that's 1 over square root of 2, which is then equal to square root of 2 over 2, which implies then that theta is going to be 45 degrees. Okay. Okay, next we have the section on matrix multiplication. So you can write a dot product essentially as a product between matrices. So you can write the dot product between U and V if U and V are both column vectors simply as U's transpose times V or V's transpose times U. And then let's look at the other two identities below that. We're going to look at the derivation of those two identities. Okay, let's look at the derivation of the first identity. So we're mixing matrix multiplication with the dot product now. So if you look at the if you look at this dot product, okay, now this is an n by n matrix multiplied by a n by 1 matrix. So this is going to be a column matrix, an n by 1 column matrix, and this is also an n by 1 column. So if you take the dot product again, you've got the dot product between two column vectors, and we know how to calculate that. But in terms of matrices, you can basically write this then as it's the same as taking the transpose of that column vector and matrix multiply it with this matrix. All right. Now, if we apply our transpose laws tell us that this can be written as this transpose multiplied by V, everything transpose. Okay, that's just an application of the transpose over a product between two matrices. Okay, so basically then what we can then write that as is you can use the transpose over that product of two matrices there. So that then becomes U's transpose multiplied by A's transpose. Okay. Multiplied by the vector V, everything transpose. Okay. Right. So what we're going to do now is we are going to group these two matrices together and apply the transpose laws. So it's going to be basically it's going to be A's transpose with V, the transpose of that matrix, multiplied by U's transpose is transpose. Okay, and that then basically is going to be this is a, what is that? That again is a column. It's a column matrix. Okay, and you take the transpose of an n by 1 column matrix, which is then a 1 by n row vector, and this here is going to be a column vector. So you've got a row vector times a column vector, and basically that is just going to be the same as saying that you're taking this column vector U and you're taking the dot product with this matrix here. Okay. Alright, so that's the dot product. So these two things are the same. Okay, the next identity is proved in the same way. Let's quickly look at that. So there you go. Basically, you take this dot product here. Okay, so again, this is a column. That is a column vector, and this is a column, an n by 1 column vector as well. We know how to take the dot product between that. But this you can write as a product of matrices. You can write it as a row vector, right? And the row vector is the transpose of this matrix, which is a row vector. Matrix multiply that with the column vector U. That gives you exactly the same answer. So then again, applying the transpose law, that's going to be U's transpose multiplied by this matrix. Okay, and that's everything's transpose. Alright, and then again what you're going to do is you're going to do a grouping together again, and the matrix that you're going to group together, the matrices that you're going to group together is basically that group there. So applying the transpose law, you're going to have the vector V's transpose, okay, multiplied by this matrix here, U's transpose, multiplied by A. Everything's transpose. So that's just an application of the transpose law. So that's going to be V's transpose multiplied by, again, that's going to be A's transpose multiplied by the vector U. Okay, so what is this? This is that is a column matrix, an n by 1 column matrix. And what is this? This is a row, it's a 1 by n row. So multiplying this together is just going to be exactly the same as taking the dot product between this column vector with this column vector. Alright, so that is just an application of matrices, writing dot products as products between matrices.